Hello.
Good afternoon, everyone. A very warm and enthusiastic welcome to all the participants joining us today from across institution and region. Hi, everyone. I am your session moderator Udayan Ghosh, Assistant Librarian at Ashoka University. We are delighted to have you with us on the second day of this exciting and future focused webinar series. On behalf of HDFC Library and Ashoka University, it's give me immense pleasure to welcome you to the session 1 of Librarian Colloquium L3 webinar series focusing on artificial intelligence, research metrics, and emerging trends. We are proudly present to this webinar series designed to strengthen librarians' evolving roles as strategic partner in teaching, learning, and research, innovation, and knowledge management. This series explores five critical domains shaping modern librarianship: artificial intelligence in libraries, research metrics and evolution, scholarly communication, science mapping, standardizing usage metrics in libraries. This series aims to strengthen the roles of librarians as strategic partners in teaching, learning, and research, innovation, and knowledge management. This series addresses the word of librarian thoughtfully divided into nine meaningful attributes, each representing the evolving roles, strength, professional excellence of modern librarians. This nine pillar reflects how librarians contribute as a leader, innovators, facilitators, and guardian of knowledge in the today's academic research ecosystem. The librarians we are splitted out nine attributes, that is L literacy champion, I for infrastructure stewardship, B for bibliometrics and impact specialist, R research communication facilitator, A open access advocate, research integrity guardian, I interdisciplinary connector, A archiving and preservation expert, N for network knowledge leader. These 9 pillars define the excellence and relevance of librarians in today's academic ecosystem. Welcoming our distinguished guests, we are privileged to have with us two eminent personalities who have significantly contributed to the world of research, data science, and academic librarianship. Our esteemed resource person, Dr. Juan Pablo Vasquez, from data scientist CWTS Leiden University. Dr. Vasquez is an accomplished data scientist and researcher with expertise in bibliometrics, science mapping, data analytics, research evolution. His remarkable work in contributing to the global enhancement of scholarly communication and research visualization. Sir, we are truly honored to welcome you today. Now I welcome our distinguished speaker, Dr. Santanu Ganguly, Director of HDFC Library. Dr. Ganguly's visionary leadership continues to strengthen academic library excellence and foster innovation in higher education. Sir, we sincerely thank you for the consistent encouragement and guidance and support in the creating such a meaningful and professional platforms for the library community. We warmly welcome both our expected dignitaries today's session. It's time to talk about today's session. We are often to talk about research data knowledge, but how often do we truly visualize them? Today's topic is highly relevant and insightful and intellectually enriching. Today's topic on research science maps for information retrieval and visualization technique. In today's data driven research world, we know the science mapping has emerged as a powerful tool to explore the research trends, collaboration networks, emerging themes, knowledge structure, and evidence based decision making. It enables the scholar and librarians and institutions to convert complex data into the meaningful visualization intelligence. What exactly the science mapping is? The science mapping nothing but a method for visually analyzing the research data into understand the structure and development of a scientific field. It's help identify the research trend and key topics influence the authors, institution, and collaboration networks throughout maps. It's simple what we can say. It is a turn large amount of scholarly information into easy to understand visualize of knowledge. Without taking much time, I now the distinct honor to invite Dr. Joan Pablo Vasquez to kindly share his valuable presentation and deliver today's keynote session on this highly relevant topic. Sir, over to you.
Thank you. Yeah, I'm very happy to be here. And I will just start my presentation right away. So today I will present my topic of research, that is science math for information retrieval. And I also will talk about visualization techniques of how to create your own maps. So the structure of this presentation will be that first, I will start touching on the conventional search techniques that people use, because I want to set a ground of why science maps are useful for information retrieval. Then I will move to what a science map is, the types, and everything you need to know. and then to the tools and data sources you can use to create a science map. And finally, we will spend a lot of time on the practical steps so people can know how to use these techniques for their own information retrieval. And the first thing I want to do is to make a little word cloud where everyone can participate, because I really want to know how people search among the audience. So I want to share interactive poll. Start presentation. So I would like people to take a screenshot of this QR code and respond what tools do you use to search papers? Like, do you use Google search or something else? I really want to know. So if people could start writing their answers here. Huh?
Nothing. Continue, please.
Okay. Co-authors. So more like the tools instead of the technique. Where do you get your co-authors from? I really want to know the name of the data sources and the tools. Okay.
I think, Pablo, your mic is mute.
Well, that's unfortunate. I was saying that I see that people use Google Scholar mostly, but also there's a lot of people that use other indexes like OpenAlex, Web Science, and Scopus. And I will guess PubMed by some of the keywords here. So yeah, now I have a good idea of the audience that I'm working with. This will help me to direct my presentation better. Thank you, everyone. So I will continue. And please tell me if I am muted again, because I cannot see when I present it.
Sure.
Thank you. So the first conventional search technique I want to talk about is keyword search, that I believe is what most people use. And this is just searching by text. At the most basic level, you can search for exactly the same word that can appear in the title, the abstract, or the keyword. So if you search for bacteria, you want to find bacteria in the paper. And then you can search for similar words. So this is a bit more complex from the side of the tool, but you still search for bacteria and it will find the synonyms. Then a field specific search. So this is, for example, when you use the mesh terms, the subject headings, where you are looking for categories of data. So for example, bacteria as an organism, but it can also mean that you are looking for journals, or you are looking for universities or for authors. So everything that is enriched data, that's field specific. And finally, the Boolean search, where you concatenate a long query and you make conditions where certain things must be or must not be, or you create more complex logical patterns. So this is the most typical thing that people do, and it's usually enough. If you already know what is the paper that you're looking for, you can find it using this. Then this is new, a large language model search, and this is also becoming very popular. And originally, at the most basic level, when large language models were created, people would just ask for a paper, and the large language model will just know the paper. It will have been trained by it. So it will have to recall it from its training knowledge. And this is where large language models will hallucinate. This was fixed mostly recently with retrieval augmented generation, or RAG, where the chatbot, instead of just recalling a paper from its own knowledge, contacts an agent. An agent is like another LLM that is trained to interact with something else, like the database. So originally, papers were indexed in a database, and then the chat will ask the agent to search for papers in the database. And then it will retrieve them and show these are real papers and summarize the content to the user. However, more modern tools, like, for example, deep search, they use more steps and more agents. So this has become very good lately. Then you have citation search. This is what people usually do when they look at the references of a paper. So there are two types of direct citations from a paper. One where you have a paper and you look into the reference list, and the other is where you look, for example, in Google Scholar, which are the papers that are citing this paper. So these are the direct citations that you see. I don't see if you can see my mouse, but on the image you have the query paper, and the first arrows are the direct citations. And then you have indirect citations of a paper. And this is already a bit more complex to do if you just want to do it with Google Scholar, but it's very good. This usually gives you very good retrieval. And you have two types. One is bibliographic coupling, where you have the paper that is in the reference list, but this paper also cites another. So what happens is that the query paper
Your mic is mute.
Thank you. Yeah, I don't know why that happens. So I believe it became mute when I was talking about bibliographic coupling. And then the mirror is co-citation. So it's the opposite. The paper that is citing your paper is also citing another paper. And what is very nice of these indirect citations is that it can happen more than once. So instead of just having a one-to-one, you will have a number of co-citations between two papers, and this can give you a score. So you can sort papers by how co-cited they are with your query paper. Later, I will show a way of doing this with code. So yeah, this is something very effective. And finally, you have recommendations, which is a more obscure way of searching for papers. So what recommendations try to do is to suggest papers to the user based on the preferences, and it combines a lot of attributes and strategies. So you don't really know why you're getting a recommendation, but on the other hand, it requires very little input from the user. So when you, for example, go to Google Scholar and you have a list of the latest papers in your field, this is a recommendation. So in summary, we have these four types of search, but something that all of them have in common that makes them a bit less useful is that they return a list of papers. And this list can be very long, right? can be so long that you cannot possibly read it. So that's where science maps come in. So what is a science map? It's a document landscape visualization technique. So what this tries to do is to give an overview of a collection of documents by projecting some attribute of the document in an image. And this is unsupervised. So you are not trying to tell the visualization what to do. You are letting the data speak for itself, which is very helpful when you don't have a clear idea of what you want. And this is also self-organized. So in theory, you shouldn't intervene how the landscape is being created because you want the landscape to speak for itself. And this has an advantage of just using lists. So if you use a list, you have to go paper by paper. But if you visualize your list or something that is bigger than your list as a science map, first you can summarize the collection. You can see the topics within the collection instead of going paper by paper. Then it can show you unexpected features of your data. So for example, you can find topics that you didn't know existed. Or if you made a search, you can realize that there's subtopics within what you are trying to find. Then it can facilitate filter out documents. So you can find, for example, topics that are really not what you're looking for, and you just remove all the documents in that topic. And finally, it suggests new search lines because of the unexpected topics that you can find. So then you can refine your query and make a new search, knowing that this new topic exists. And there's, in practice, when you do a science map, you have 3 types of science maps based on the unit of analysis. You have the science maps that try to study the documents, the ones that try to study the authors, and the ones that try to study the keywords. So all science maps are created based on documents, but the difference is the unit of analysis that you try to visualize. For the purpose of information retrieval, I will focus on documents because that's the ideal science map for information retrieval. Then, when you visualize the map, you have to make a decision of what the nodes, for example, there you see a map, what the nodes represent. So each of these dots is a document or is a group of documents. Here, each dot in this image is a document, and you can see it's already getting very unwieldy, very hard to read. So when you have too many documents, it's better to put them all together in a single node, and then your map becomes more readable. In this map that you see, also you see colors. These colors are the clusters. So if we want to make this into a cluster-based map, you will have just 5 nodes. It will be very easy to read. Then, on which attributes you base the science map? You can base it on the citations between the documents, and you can base it on the text similarity between the documents. And here you have many ways of doing this. So for citations, you can use the direct citations, or you can use the co-citations or the bibliographic coupling that I showed earlier. And for the text similarity, you can find if the same word is on both. That's how it used to be before, co-occurrence of words. And nowadays, you have text embeddings. So just to make a short summary of what a text embedding is an artificial intelligence technique where you try to represent the meaning of a text. So instead of just having the text, you will have a vector. This is a series of numbers. How you generate these numbers is very similar to an LLM. So I will not go very deep into how these are generated, but what they are supposed to mean is what is the meaning of the text. So if you have two vectors, two series of numbers that are very close to each other, that means that the text they are based on is also very similar to each other. And then how you represent the data, you can either do it as a network or as vectors, as I just explained. The traditional way of doing this is networks. And then, for example, you have networks of citations between documents. And then this network, you can just project it, as you see in the map, or you can cluster it with algorithms that find communities inside the network. And how do you use the map? There are, depending on the task that you want to do, you can use it in different ways. The most simple way of using a map is by just looking at it and exploring it and understanding what the map is trying to show you. So in this case, it is more of a browsing, understanding task. And then if you know more about what you want to see in the map, you can do more direct search. So what you can do, for example, is in the map, find the papers that you want to, that you already know. So you know these papers are relevant for your task, you find them in the paper, and then you look at the papers that are around the papers that you know. The other thing that you can do is to just look for keywords and see where in the map these keywords are. I will show later how to do this. Then the other task is delimitation, where you want to work with the clusters in the map to identify which of these clusters is really the search need that you have. And finally, iterative clustering. This is a bit more complex, but what happens with science map is that the position of everything depends on the context that you have. So if I take half of the documents in the map, the clusters will be different. So for example, you can have a science map with all the papers in the world, and it will show you the biggest topics in the world. But the topic that you are looking for might not appear because your topic is a bit more niche. And generally it doesn't appear because the needs of real people are never so general that you can find a cluster in a global science map. So you need to do a bit of filtering. So you will remove some of the papers and run the clustering again, and then you will start to see that your topic starts to emerge. And now I want to talk about the tools and the data sources that you can use for making your map. So in the word cloud that we did at the beginning, we saw many of these data sources. So you are all familiar with them. But what you need to make a science map is to have not only one paper, you need to have a lot of papers, sometimes a million papers. And not all these tools allow for that. The most reliable ones that have the highest quality are Scopus, Web of Science, and Dimensions. But these are all paid, and they have an export limit. Even if you're paying, you cannot export a million papers at the same time. Something that is very nice of these data sources is that they also have the citation data, which is hard to get by in general. Then if you go to the free options, you have the best for science maps is OpenAlex because it's the most complete one. And also allows you to export bulk of data and it's very flexible. Then you have Semantic Scholar. It has less coverage than OpenAlex, but it includes the semantic embeddings. So you can already do text similarity maps without having to generate your own text embeddings. And finally, you have sources that just give you single documents. So these are not very useful for making a science map, but it is sources of papers that you can still use. And then if you have a reference manager, you can also export the papers that you have stored there. And sometimes you have so many papers that you can already make a meaningful science map. And then the tools. So I divided the tools in two. The ones that have integrated data sources, that is, they can connect on their own to any of the data sources that I mentioned before, and the ones that are not integrated. These are tools that you have to upload your own data into the tool. So for the integrated, the most famous one is Boss Viewer, which also has a very complete source of connected data sources. I will go deeper into Boss Viewer by the end, but this is not just citations. It allows you to do a lot of things. And then you have these other sources that are web-based that I know a lot of people use. And they do citation networks. So usually you give a paper to these sources, to these tools, and they find all the connected papers, but they don't visualize all the connected papers. They have some agency on how to present the data to you so you don't get overwhelmed, which is nice because it's optimized for a user that just want to find related documents. But it's not nice in the sense that then you cannot take this data and do your own maps. And most of them use Semantic Scholar for this. Then in the non-integrated data sources, you have some tools that are dedicated for science mapping, like SIGNET Explorer and SiteSpace. I believe SiteSpace is the most popular after PostViewer, but you have to upload your own data. Then you have generated network tools. These are tools that are used for network science, but you can, if you have a network, you can visualize it there. So you have to work on the network before you upload it there. And then you have code libraries that are dedicated to bibliometric analysis. This really requires you to write some code, but they are really powerful. And you can also write code such that the API is integrated into the tool. And now I will talk about practical steps. So I will do get out of my presentation and go over several things that I have prepared. The first one is how to do co-citation search. I have prepared a code here that I will share with everyone so everyone can use it. And I believe this is the most easy tool that you can use already if you want to use citation search. I will show now how to use it. So this code is an SQL code intended to be used in Google BigQuery. Google BigQuery is a platform of Google that contains relational databases, and my institute recently uploaded OpenAlex into Google BigQuery so you can query it more easily. So we have this project where we have this database. So this is the documentation, but what you want to do is to go to Google BigQuery. So everyone with a Google account should be able to do this. And Google gives you each month, I believe, a terabyte of free search capacity. And here you can write your code. That is SQL code. And here you just copy this that I share and paste it. So all of this part is not necessary. This is just the instructions. And here you write the ID of the document that you want. So how do you get this ID? You go to OpenAlex. And you search for the document. So for example, I don't know, this paper. And you have to open it, like to really open the page of the paper. And this is the code that you're looking for. This is the ID. So you replace it here. And you can also add more if you want here. You just have to remove this here and keep the comma. So what this does is that it finds the papers that are citing this paper, and then it finds the papers that are citing those papers and makes a sorted list where the score is how often this happens. And this is what you get. It is faster when you have a paper with less citations. Yeah, so you get a sorted list. So it found this number of papers. The citation frequency is the score that you are interested. So in theory, this paper is the most related to your paper. And that's how you can search for papers here. So then if you want, for example, well, this paper doesn't have a title, but it still have an ID. If you want to check any of these papers, you just grab the ID and you paste it here. Yeah, doesn't have a title. But you can go to the page of the paper. This is the paper that it found. Yeah, so everyone can do that with the code I share. I hope it's useful for you. The next thing I want to do is to show how to use Boss Viewer. I will show how to download it first. So you just download the version for Windows or whatever you need. And it's important that you download it because there's an online version of Boss Viewer, but that doesn't have the API search function. So once you download it and you extract it, you just open it. And this has already API connected. So you don't need to upload your own data, but you can. Both Viewer can do a lot of things, not only what I want to show now. So you click on create a map based on this. And you select data through API and search query. This is the best option. And here you select your data source. So let's use OpenAlex. And here we need this data. You can also search just by text. But let's say, for example, we want to make a map of a journal. Okay. So we need the ISSN of the journal. This is the ID of the journal. Every journal should have a ISSN. So we go to Scientometrics, for example. And we look for the ISSN. There it is. And we search. And now it's downloading these papers. And that will take a while. So I will continue with something else in between. I also have created some tools of my own that are available for everyone. And the one that I really want to show is this one. This one creates science maps. And here I have some demo data where I can show you already how it works without having to have your own data. So this tool makes maps based on citations, okay? There it is. And now you have to run the clustering. And I will just use the default. So I am asking 10 clusters from this tool. It says I found 9,000 clusters. I'm going to merge them. And this is the visualization. To see what each cluster is about, you just move your mouse over here. It tells you the top 3 papers from each cluster and the top 5 keywords. And you can modify this. You can ask for more keywords or more papers. You have a lot of control over this. And then you can select the clusters that you like. So let's say you like this cluster number 1. And I would call this, I don't know, first collection. And I will save it. And now it is here. And I can choose it to create a new map. So now it's taking all the papers that were in cluster number 1 and making a new clustering. So this is what I mean by iterative clustering. You can filter out things or add more things until you find the clusters that you are interested in. Here you can also change the number of clusters that you ask and the resolution. The resolution of the clustering is a value that is specific for this clustering algorithm. It's called the Leiden algorithm, which is the most common clustering algorithm for science maps. So I believe it is worth understanding what it does. And what you want to do, and the only thing that you can control is the resolution value. And higher resolutions tend to make smaller clusters. So here you have that some of these clusters are really big, and this looks really bad. So you want to increase the resolution. Or you can also have less clusters. And then you run it again, because you still have the save data selected. There it is. We are still on that set. Yeah, and now this looks much better. So how can you find this tool? Well, I have all the tools I have created here. I will share it in the chat. And the one that you just saw is SciMacro. So this is the link to the live demo. And this is the link to the GitHub. So now let's go back to Post Viewer. It finished downloading all the papers. It found 8,000. And probably we have to remove some of them because this is too much. So here it tells you which type of analysis you want to do. And what this means is more or less the unit of analysis that you want. So if you do co-authorship, it will analyze authors. Co-occurrence, it will analyze words. And you want to do citations, analyzing documents. Okay. And then it's asking you, how do I filter this? Because it's too many. So this is just the first round of filtering. So it's not necessary that we do something. We can do it after this. And here, this will set the maximum number of documents to visualize, sorted by number of citations. So the documents with few citations will not be visualized. And after we click next, we can remove one in particular that we don't like. And then we render this. It will tell us there's one document that is not connected to the other? Do you want to visualize only the ones that are connected? Usually it's better to say yes. Otherwise, it will take longer, and then the document will just be a node that is connected to nothing. So this is a science map of the journal Scientometric. This is the top 1,000 papers by citation count. And you can see it's a bit also crowded. So a lot of things going on here. You can do some things to make this look a bit cleaner. So that's better. The colors are the clusters, but the notes are papers. If you click on one or just move the mouse over it, well, if you click on one, it will open it. But if you move the mouse over it, I cannot move the mouse, so you just have to follow what I say. At the bottom, you have a box with the data of the node, and it tells you the authors, the title, and the source, and the year. The colors here, as I said, this is clustering, but you can control it. Also, this is the Leiden algorithm. You can say, well, I want less clusters. These clusters are too detailed. So you can lower the resolution to have bigger clusters. And you run this. And this tells you, well, if a cluster has like 10 documents, merge it. There. So now it's a bit easier to see what's going on. Then you have this overlay visualization, which for the API search that we did, contain the publication year. So we can also know which areas of the map are newer. And I believe that's the most important thing that you need to know from Boss Viewer. You can also play with the layout. So this will change how expanded or contracted the nodes are around each other. But it's just for aesthetics. You can also export this. They use what is called a Boss Viewer map file. So I will just call it map. And we're not really interested in the network. And what is nice of this, save it here, is that then you can use it to see to which cluster each of the documents belong. So normally you would like to you open this on, yeah, I will just open it on Excel. Or something like Excel. Yeah, it's a bit tricky, but what I really want to show you is that the columns that you had here, one of them is cluster, okay? It is a number, it's the same number that you saw before. Number 2, number 5, number 8. So there you have a easy way of clustering that you can just use Boss Viewer for this. I believe that's the easiest way of clustering that you will find on the internet because you already have the API here. And before we run out of time, I also want to talk about text similarity clustering. So to do text similarity clustering, ideally you want to generate embeddings, okay? How does an embedding looks? It looks like this. It's a series of numbers, usually between 1 and -1. And in this case, each line has 700. So you don't really want to look at this. Just know that this is what you need. And how do you generate them? You need to use typically a BERT model. So the best one for papers is this one. This is a model that was trained specifically to work with papers. And what you have to do is to give the title and the abstract to it, and it will generate an embedding. These are all the instructions on how to do this. And yeah, it can look a bit intimidating, but you can ask, I don't know, Cloud to write the code for you. It's really simple once you do it once. And I also made a tool that can do this for you. Have it here. So what you do here, for example, is that you upload your data. That's how the tool looks. And you start here, and you upload your data. It needs to have this shape. And I have a demo here that you can use if you don't have your own data. So you have the ID, the title, and the abstract. And this can take a while, so I will make this smaller. I will just have very few lines. Yeah, so that will take very little time. And I will upload that. And I run it. Yeah, that was fast, and that gives an error. Yeah, that's not ideal. Sorry for that. But this is the GitHub code. If you know how to code, here is everything you need. You can just copy my code and use it yourself. Here is where I load Spectre 2. And once you have this, and this is something I believe is worth talking a bit about, there are two things you can do with this. You can do a network. Here. No. Here. Sorry for that. Yeah. You can do a network similar to a citation network. Or you can do dimensionality reduction. I will show how this looks because I already have the embeddings prepared. So this is the network creation part. And what you want to do here is to get the cosine similarity between every pair. Cosine similarity, to make it simple, is a way of calculating how similar two vectors are. And it's what is normally used for. I will answer the questions at the end, so don't stress. Yeah, embedding, yeah, sorry, cosine similarity. And you can calculate this between every pair. And this has a problem if you want to make a network. The problem is that if you make the cosine similarity as your edges, this will be a network where you have links between all the papers, and that's just too much. That will destroy the clustering algorithm. So you set a limit per node. You say for each paper, I want the, for example, top 20 most similar papers. And that's what you can control here. Usually 20 works well. You can play with building more or less. And then this builds a network. I can show you how it looks. So it tells you from this node to this node, this is the similarity. And then you can just use this to build a network in PostViewer. Let me show you. So you upload the files you just created, the network. And then you need to upload the original file because it contains the titles. So you have to upload it just so the visualization looks nice with the titles. Papers are here. And this directly generate a map in PostViewer. So it's against telling you there are some nodes that are not connected. Let's not show them. Yeah, and this is how it looks. So this was done without citations, using only text similarity. And the online Boss Viewer version also has many of the features that the local Boss Viewer version have, but it doesn't have the API. So it's very handy. And then you can share this. You can click here, copy, and then you send this to anyone, and they can see the same map that you are seeing here. And the other thing that you can do with text similarity is instead of making a network, you can make embedding space reduction. And this, I personally prefer because it's closer to what the embedding is. The problem is that this, because it's not a network, you cannot mix it with citations. And also in bibliometrics, everything is made so it's all about citations and networks. So it has that problem that you cannot really use the software that already exists for working with your text similarity. But I believe it's an interesting option. And usually the visualizations are better. So I will show you. The first thing you need to do here is to generate the coordinates. So instead of making a network, like we did here, we will get the coordinates using a dimensionality reduction algorithm. It's called UMAP. You just upload the same embeddings as before, and you have these two parameters to control the coordinates. This will control how far or close to each other the coordinates are. If you make it too small, all the nodes will be one upon the other. And the number of neighbors is how many neighbors you consider during the dimensionality. So if you make this number too big, it will consider all the map at the same time, which creates dimensionality reductions that don't look very meaningful. So this is just a list of coordinates. It has the ID, the X, and the Y. And this can also be uploaded to PostViewer. And this again, the titles of the papers. Yeah. So the two maps are kind of similar. Like one is the flip of the other. And also when you do text similarity, at least the way I did it, I didn't run clustering because this is already a experimental technique. I didn't want to build too much upon it. But for example, here, this is obviously a cluster because they are so close to each other. And let me show you a map of how this can look. So this is a map that was made by other people. It was done with with text similarity, but it was done into a network. But I want to show it anyway because it looks very similar to the concept I just presented here. And here, each node is a paper, and they do some labeling for areas of the map. And even as you don't have clusters, like the colors are not clusters, they are gears, you can see it like this is obviously a cluster, right? But you don't have the problems that you have with clustering, that you have to put everything somewhere. So for example, you know that these papers, they don't belong anywhere. They are like here in between. So you don't need to force them into a cluster. I can also share this in the chat because it's a very nice tool. And yeah, well, I had something else to show, but I believe we ran out of time, and it's better if I start answering questions now. So that was my presentation.
I request all of the participants, you have any question, please raise your hand. Otherwise, type in your chat.
I believe one person has the hand raised. I can start answering the questions in the chat too. So it is required hand of practice. No, not really. You can. I believe after 1 hour working with this, you already become very skillful. Wait a second. So I would say don't be afraid. Just go for it. To Panduranga. Then to Pranit Lanje, does data cleaning of any sort is needed before processing? Yes. If you don't clean the data, you will probably have a lot of papers that don't have citations or papers that don't have titles, and this is just noise. It would be better to remove them. You can also have problems with papers that have too many citations, but I will just leave them there. So I don't think you need much cleaning. What can happen if you are exporting this data between many platforms is that you have problems with the text because they are using characters that are not ACII. You can remove those, or you can fix it with encoding, decoding with the UTF or Unicode. That's the only thing you need to do. Then, if one is doing a systematic review, is it better to start with regular structured databases and then use the mapping for more literature? So I would say it's better to start with the structured database, but that run a risk that you don't find the papers that are kind of away from your field. So let's say you have a community that is working on a topic and they cite each other, and it's a field. And there's another community that is working on the same topic, but they never cite each other. If you start with the structured database, you might lose all the papers from the other community, and then you will never know they existed. But I don't think that's very common. I believe if you are very generous with the first collection, like very high recall, low precision, this should be okay. I hope that answers the question. Share kindly. Yeah, I can share this as a PDF, no problem. Any Python tool you suggest for data cleaning? No, not really. Data cleaning is really easy. You just, if you have problems with the title, you just use the string encode, string decode function of Python, because there's not really much to clean. There's not many problems that you have to deal that require a specialized tool. Hi, could you please share your views on Google Scholar Lab as a research retrieval tool? That's, I believe, is a DeepSeek tool. It's quite good, but it's the same as any other DeepSeek tool. It will just find a few papers, and that's it. And the problem that you have there is that you don't know what happened behind. You don't know what you might be missing, and that's a problem I have with searching papers that way. So what I will do, I maybe use Google search, Google Scholar Labs as an initial search set, but expand it a lot. So the papers that Google Lab found, you know they are relevant. So then when you have a lot of papers and you make a map, you can see where the papers of Google are. And then you know, okay, I know this area of the map is supposed to be relevant. So I will look in this area. It can save you a lot of time.
Okay, great. I think we'll move forward to our next speaker.
Okay.
Thank you, Dr. Johan, for extremely tremendous informative session. Now I invite invite Dr. Santanu Ganguly to kindly share his valuable insight on today's topic. Over to you, sir.
Johan, thank you very much. Let me share my presentation quickly. Let me know if you can. Thanks, Pablo. That was a wonderful session. I really appreciated. Thanks for accepting our invitations and to be a speaker, and also showcasing the different areas what you have shown in this particular area. Dear participants, I think Pablo has already. I just want to know, can you see my screen now?
Yes, sir.
Okay. So what I would be doing is I'll be quickly run through a kind of a basic informations on the science mapping, because I myself do a lot of science mapping using several tools, and which are applications which are available, but I've never used the platforms which Pablo was showing, but I have used extensively the WAS viewer actually. So what my sessions will cover is basically a simplified versions of what Pablo was talking about on science mapping, the visualizations and the storytelling part of it. As we know that there is an ever-expanding universe of science is coming up, and how the relentless growth of scientific output is reshaping the way we discover, organize, and understand the knowledge. So the exponential growth is for in the last scientific literature doubles almost 9 to 15 years, with over 1 million articles are there and published annually in the field of biomedicine, in the life sciences alone. And staying current is no longer a matter of effort. It requires an entirely new tools, new strategies to, keep in touch with the different areas on the biomedicine and the life sciences areas. So one of the important thing is we would like to understand is there is a scientific deluge is there. So millions and millions of people, countless connections are there, impossible to navigate a map basically. So the need for navigation is you have the overwhelmed stakeholders like researchers, managers, and then you have the essential for progress. So navigation tools are critical for stimulating the collaboration, the fostering the exchange, and then the beyond the bibliometrics, which in a very detailed way Pablo was talking about. Now, introducing the science map, so turn the abstract scholarly data into a much more explorable, navigable, and a landscape of knowledge. So that's a very important area we need to understand. So, what are exactly the science map is? First of all, we need to understand from a basic area. It is a graphic representations, it is a navigation tools, and it has got a strategic lenses where support the institution, the funders in understanding the complex research landscapes and making informed decisions on these areas. In fact, these three fundamental pillars are very important as well as when we talk about the science mapping is concerned. Now, if you are into a great explorer, needs a map, science maps gives you the researchers that some power of orientations on the particular subject area. So the power of visualization plays a very important role. Visualization is more than aesthetics. It is a cognitive tool that transforms the raw abstract data into an actionable insight. In fact, I just saw that a lot of data was, collected and accumulated by, Pablo, and then he was giving a complete visualization of that using the Vox Viewer model. So reveals on hidden structures and emerging research clusters. In fact, those who are into writing, review of literature, or you are doing a systematic review, or you are doing a meta-analysis, or you are into you want to find out something related for the funding proposals of the bilateral or multilateral organizations where these kinds of visualization tools plays a very, very important role. I have been using this very extensively on many of my proposal actually. Exposes a gaps where knowledge is thin or missing, support a strategic thinking and evidence-based decision making is a very important of that. Now, tools of the trade is mapping methodology. So you look at the techniques that run scholarly literature into visual, navigable, and knowledge structures. So already you have seen there is a co-word analysis is there, that how keywords and the phrases and the co-occurrence across scholarly papers to identify the relationship between the research topics and revealing the intellectual DNA of a particular field actually. Like for example, there is a case study by Fleming Scoff where applied his techniques on the map on biological research at Aarhus University, surfacing the hidden thematic clusters into that. So what he that he collected the papers, he extracted the keywords, he measured the co-occurrence, he built the network graph, and then the cluster research themes across this for the better descriptions and all. So if you look at the SCOVE science map, a complete case study on this area, so you will be able to understand exactly what I am exactly talking about here. So here the data collection took place. So 6,830 papers from the permanent staff of Aarhus University's biology department. Then the keyword extraction was done. A cognitive mapping was created on a research identity and topical clusters of the institution. And then the Python workflow took place on by data retrieval, data cleaning, analysis, and final visualization output and all. Somebody was asking a question. I think it was Mr. Shukla was asking whether I don't know that whether data cleaning is required or not. I said yes, data cleaning is required, and before even you do the visualization, you need to have a proper data cleaning. Otherwise, you may fall flat on your face, the some visualization comes up and it talks very different, so you get completely flabbergasted out of that. Mapping the research DNA, so each cluster reveals a distinct strand of scientific identity, how a community thinks, publishes, and connects with each other. So, visualization, the research landscape is like topics and the papers. It is the journals and the groups, the journal research groups or departments to pinpoint overlap and the specialization. And third is the connections. Understand how seemingly underrelated research areas connect and influence one another over time. So you need to have an interactive exploration, like navigating the map, how static diagrams to living, breathing, interactive atlases of the global science you can showcase at some places. Like, for example, the ETO's Map of Science, a global perspective on research, which is basically nothing but an emerging technology observatory map of science, organizes hundreds and millions of scholarly publication over 91,000 research clusters. And if you go to the website, you will see they shows the revealing the key trends, what are the hotspots, what are the emerging concept across global science and technology. Everything is given on that particular thing. So you can imagine the how much amount of data is basically put together so that they can have those research clusters and research dimensions can come out of that. The world of science is at your step. So every connection, a collaboration waiting is always happening is there, but filter by discipline. So that is narrow the results by field, emerging technology category, or predicted growth trajectory. So you need to have this. So these are the pinpoints, the hotspots. Identify where the research activity is accelerating and where it is slowing down or stagnating. The multiple views like switch between map, list, and summary views to extract different layers of insight from the same data. Interacting with the clusters like Hover's Preview or Click Explore or Zoom Dive, the interface is designed to progressive disclosure, letting users move from a bird's eye view overview down to individual papers and researchers at their own pace. Then comes your biomedical frontiers, which is a very big area, as I mentioned earlier. A deep dive exploring one of the richest and most complex domains in all of science, actually. The landscape of biomedical research, in fact, a comprehensive visualization of 21 million scientific papers are there in PubMed, spanning the full length of biomedical and life sciences fields. And the sheer scale reflects the extraordinary pace of modern medical discovery. So PubMed's database alone grows hundreds of thousands of papers every year and making a visual navigation almost indispensable. And there is a large gamut of people and the researchers. In fact, I worked very closely with the different doctors in this area during my tenure at All India Institute of Medical Science in AIIMS, New Delhi, where we used to bring out the biomedical research in a much more visualization format on a various topic level. Say, for example, say something on neonatal disease or something on more on mouth ulcer, that is called, or maybe something on the oral cancer. Some of these areas we have really worked very closely and we have pulled out the data from there and we have worked significantly on these areas. Mapping life itself, so basically 21 million papers. Every dot here which you see in the diagram is a study, and every cluster of field that may one day may save a life. So you can imagine why the clusters, why Dr. Pablo was emphasizing on the clusters which are made and the clusters which get disintegrated, or the clusters which are not coming into that particular ecosystem which he was talking about. So because these clusters which are formed or thing, I'll show you some of the very interesting examples where how these clusters play a very important role in these areas. So unveiling the research trend. So what you have, identify the emerging areas, spot the nascent research clusters before they become mainstream, a critical advantage for early career researchers. Track the field evolution, watch how disciplines like genomics, immunotherapy, CRISPR is that there was a Nobel Prize was awarded on CRISPR, which is used as a gene editing purpose for the Jennifer Doudna's research is on that area where it is used basically on the gene editing processing. And so these are some of the evolutionary areas are coming up in a very big way. And understand the dominant themes, like recognize which areas command the most attention and resources, and ask whether the emphasis is warranted or not. Paper level detail, yes, science maps are not just panoramic. They support granular exploration at the level of individual publications. Like mouse over reveals paper title, journal, and publication year instantly. Clicking opens the full PubMed record for in-depth reading. Direct access to primary sources bridges the gap between the map and the knowledge. Now, one of the important area where I basically come from is basically from data to narrative. The art of storytelling, because the most powerful maps don't just show where things are, they tell you why it matters and why it has captured that particular place in that, so that it shows into it. So science maps are not just charts, they are stories waiting to be told. The visualization provides the plot, the researchers are the characters, and the data is the setting. In fact, I've developed a model which is called as a DAVE model, data analytics and visualization experiment, where basically during my different training programs or workshops, I generally when I use that, I do a lot of hands-on trainings with the people to create stories from the data which is there. So transforming the dense technical findings into accessible narratives, make science legible to the broader audiences from policymakers to the public, and amplifying its real world impact. So it is a journey actually, if you look at it. So it is from data to discovery to dialogue. So the journey from raw numbers to human understanding is the most important journey in the science communication today. Strategic thinking and reflection. So strategic maps are uniquely suited to support both top-down strategic planning and emergent discovery-driven thinking that can create a space of reflection on where a field has been and where it should be. It guides an institutional research fair of the roadmap, fuel the creativity by surfacing unexpected connections, and enable honest assessments of progress and gaps. The human element in science mapping is key researchers. So maps identify the individuals driving the breakthroughs, making invisible contributors visible. It also brings in the collaboration networks. In fact, many of my projects which I would be submitting in the different bilateral multilateral organizations where one of particular area, say for example, my university or institute is working on a particular area, how it is getting connected to the other organization or institutions on the same framework and all. I remember when I was talking to one of my friend from Germany called Klaus Tochterman, when he was delivering a talk on Science 2.0 in one of my events. So we had a detailed discussions on deliberations on how the collaboration networks and the social architecture of the scientific progress takes place in these areas. And it is behind the discovery that every data point represents a person, a team, a life's work. A maps helps us honor the human story. So the real world impact and applications are science maps move beyond academia to inform decisions and shape the research investment policy and innovation at scale. So guiding the research investment, so science maps provides funders, institutions and governments with evidence that to make smarter, more strategic investment decisions in research. I'll give you an example. I was working with Research Council for UK government, where in one of the projects it was on water, energy, food nexus. So I worked on extensively on WEF, and where in the WEF it was mentioned that which are the primary organizations or institutions in the country who are working on these three nexus. If you touch upon water, your energy and food get affected. If you touch on energy, your food and water get affected. If you touch on the food, your water and energy get affected. And so we developed a complete policy document on this and submitted to the RC UK government that where exactly the research investment should go on, how the funding should be, provided to the entire gamut or to the respective several institution or organization where the research is taking place. So we did a huge amount of research through secondary research, obviously, which is and in some places in the primary research. So we brought a blend of both, and then we developed that entire documentation. So it was based on these four parameters like growth rate, the gap analysis, the strategic alignment, and the collaboration potentials and all. Now, investing in the future of science, so map landscape first, the place your bets with confidence and evidence, fostering interdisciplinary collaborations. It breaks down the silos because in many organization institutions, it has been realized that they don't communicate. So you have to unlock the collaboration that would not otherwise happen. You need to cross-pollinate the ideas. So one idea is there and the other idea, so probably those two can come together and can evolve the third idea, which could be maybe something very unimaginable. And it also drives the innovations at every stage. So for interdisciplinary research, like in Ashoka and all, these three things are very important as far as the visualization is concerned. For example, I take an example in healthcare sector where there is an artificial intelligence in medical research is humongous. We have to identify the clinical applications like diagnostics, the drug discovery, the personalized medicine and all, and surface the emerging challenges around data privacy, the model bias, and the regulatory approvals. Facilitate collaborations between the computer scientists, the clinicians, and the ethicists. So in some of the AI applications and all, like for example, when we talk about this, some of the areas like GDPR, how much the different nodes in a network are aware of the GDPR aspects when you are doing a global aspect of that. So these are very, very important areas to emphasize on it. The future of science mapping and visualization is mammoth. Emerging technologies are coming, and I will be showing you some of the best of the tools and the technologies. You have already seen Dr. Pablo's, he has already shared with you the platforms which he has used, but I'll be also sharing you some other platforms also. So there is an AI-powered mapping, there is a real-time integrations, and there is an enhanced interactivity is coming up in a big way. So the next frontier of discovery is nothing but your science mapping is coming up, and that is an intelligent mapping system which is coming up in a big way. Democratizing the unscientific understanding. It transforms the technical literature into navigable, intuitive interfaces. Empower the journalists, the policymakers, the citizens to engage meaningfully with science. And bridge the persistent gap between the scientific communities and the society at large. In fact, here I would like to mention there is something called as a quadruple helix model, where you have the academia, the industry, the governments, and the civil society. They are all entwined with each other. To have a democratization of the scientific mapping which is coming up, we need to understand these concepts. So one of the important areas, storytelling as a core component. So you need to have a narrative power. How do you scientific breakthroughs communicated in the form of stories? So the common man, we have created the visualization, but a common man, how will he understand from the designs? Visualizations has to be there in such a way that it can create a story, and then the public engagements. So challenges and considerations, yes, science mapping is powerful, but not without pitfalls. Understand its limitations. It is important as appreciating its strength also. Data quality and the biasness. Sometimes selection of the keywords, the non-English literatures are there, the transparent, reproducible methodology is essential to maintain the credibility. In fact, this diagram, this fishbone diagram, clearly gives you where is the convergence of the biasness, where is the keyword biasness, where is the regency biasness into that, and it can improve the science mapping into that. So I'm not saying that a science mapping is a foolproof system, no, but you need to be intelligent enough to understand and find out the misleading areas also. The devil is in the data. That is called GIGO, garbage in, garbage out. Even the most beautiful visualization cannot rescue a flawed data set. Interpretation and oversimplification. So simplification risk, experts interpretation is required, and balancing the clarity and rigor. So ethical implications, so you have to have a responsible use. Avoid misuse of these kinds of maps also. And upholding the integrity like open methodologies, transparent data sources, and community oversights. So in conclusion, I would say that embracing the visual revolution, a new era is how humanity understands, shares, and builds up upon the scientific literature. So scientific maps, more than just pictures, they are essential like navigation tools. They have a transformative perspective, and they have an accelerating discovery. So the power of narrative in science is it humanizes it. When data is wrapped in narrative, it moves people to act, to fund by the funders, to collaborate or co-create, and to believe in the power of inquiry. So this is very important. We need to understand. So a call to action, explore, navigate, and then you tell your story. Interactive demo exploring a science map. So when you do it, you will see a lot of tools which I'll be recommending. Already Dr. Pablo has given you the thing. First is that you open and launch a particular thing, browse, zoom out to view the clusters, apply different disciplines and growth filters, and click a cluster for your papers and authors and all. So what most important is science mapping and visualization tools. It is categorized into 4 categories. Please remember, all tools are categorized into these 4 categories. Science mapping had got certain bunch of tools. Network and text visualization, like he was showing that text mining, I was seeing that text mining and similarity text and all. So text network and text visualization is there. Bibliometric and citation is there, and then the utility tools are there. So quickly I will run through this. Like for example, there is a platform called Alluvial Generator, BibExcel, Bibliometrics R package, which is very popular, I find. Like for any co-citation, coupling, scientific collaborations and all, Bibliometrics R package creates a very, in fact, our studio has got a complete package. You pull out the data from the Scopus, you pull out the Clarivate analytics of the Web of Science, and then you use that. In fact, one of my colleague from my for my department, she has used extensively these platforms to create the visualization for many of my research output of my university and all. SiteSpace is a very powerful platform. SiteNet Explorer is there, visualizing, analyzing citation networks of scientific publication. HistSite is developed by the Thomson Reuters, which generates the historiographic diagrams of the direct citations. IDR user maps and novel approach to visually looked into. It was developed by Georgia Tech University, IDR. Then you have Pageek. Pageek is a pioneering tool for the analysis and visualization of large networks. Pageek word stands for spider in a Slovenian language. So it is fitting a tool designed to untangle and map the complex webs of relationship. You have a Sci2 tool, that is a science of science tool, is a modular tool specially designed for the study of science. So it is a very interesting tool I came across, science of science tool. Shimago, I am sure all of you are aware of, that is the shape of the science, journal and the country ranking and all basically. Then Scholar Tree, which is hosted by the UC Davis, and they provides a tree-based visual interface for exploring the scholarly relationships. Software and data of Ledistorff, which is creates a series of tools for analyzing the publications, the patents, and this is the platforms which is suite covers cohort analysis, journal mapping, scientometric indicators while used in the science of science community. Voxviewer, I think he has taken it up extensively. It was developed in the University of Leiden by one of my friend from the Germany. Science mapping tools, summary. So I talked about these 4 platforms: Alluvial Generator, BibExcel, Bibliometrics, SiteSpace, SciNight Explorer, Crexan, Sci2 Tool, Shimago, Let's Draft Tools, and Vox Viewer. So these are the tools which are there. Now I come to the bibliometric citation and usage tools. So stands one is the Google Scholar is the number one in that. Mendeley, I'm sure many of you are aware. Microsoft Academic Research has come up. They have also doing a lot of work. In fact, they are implementing a lot of AI into it already. Then there is a Publish or Perish is a free software, which is it is available at hazing.com. You can use that. Semantic Scholar is an AI powered research tool. And then bibliometric and citation tools at a glance like Google Scholar, Mendeley, Microsoft Academic, Publish or Perish, Semantic Scholars are there. Network tree and text visualization, if you look at, so Tableau is a very important platforms which is extensively used for data visualization. It has got a priced model as well as the public model. So public model, if your data is not confidential, you can use the public model because all the data gets stored in the cloud actually. So network tree and text visualization like Carrot and Foam Tree, which is a carrotsearch.com or a JavaScript based thing. D3JS is once again a JavaScript based library for manipulating the documents. It has got a facility like interactive web based visualizations, binding data to DOM elements and applying data driven things. Ggobi is a open source visualization platform for exploring high dimensional data. Gephi is a leading visualization and exploring software for all kinds of graphs and networks. Jigsaw is a visual analytics system which is from the Georgia Tech, and it explore, analyze, and make sense of document collections. NodeXL is a free open source template for with use, which collaborates with the earlier Microsoft Excel 2010, 2013 till 16. They used to use it, NodeXL, and imports the social media data now and calculate the network metrics and all those. Raw is a very important thing, which is easy to interactive tools is there. Sequoia View is also a tree map visualization tool. Then your tree map is a space constraint visualization hierarchical structures. You can see the diagrams, how it develops. It was developed by the University of Maryland. Walrus is an interactive visualization, large directed graphs in 3-dimensional space, which you can develop. It gives out a very interesting output of that. WinDirect Stat is a software published in GNU General Public License version, available in that. It is a free software, WinDirect Stat. So this is a complete overview of the network and the visualizations tools which I just talked about. Now, if you compare these key visualization approaches, so graph and network tools, you can use Gephi, NodeXL, Pajek, Walrus. For tree map and hierarchy, you can use Foam Tree, Sequoia, Tree Map, or WinStar. Interactive and visualization, you can use Tableau, D3J, and Raw. And for knowledge metrics, it's available in the Mariam. It is developed by the KISTI, that is the Korea Institute of Science and Technology. They have used it. I find it a little difficult in using this. I was going through it, Knowledge Matrix Plus. Want to use it for some other knowledge management purpose. WOS Download is a utility tool to facilitate the downloading of the Web of Science database. It is for scientometric analysis. Utility tools like Knowledge Matrix and WOS Download I have already talked about. So experience the map of science, and the best way what Science Map can do is to one yourself. So sciencemap.eto.tech to begin. You can start there. You can visit the website and you will get a lot of information. But I would like to tell you that there are certain platforms which I extensively use for my current research work. That is, one of them is called Open Knowledge Maps. It was done by one of the, I think, Sweden-based scientists. He has developed that. Now, here you can see for each and every paper, they have used the ontology which was used, that it has created a bubble out of it. So the bigger the bubble, based on the keywords and the keyword analysis, it created the size of the bubbles. And it shows that these are the papers which are there. If you click one of them, it will give you what are the list of papers along with their abstract and metadata is a part of this. Then another platform I use, which is for connected papers, which has got different areas to look into for the research purpose. The third one is obviously is the Research Rabbit. I'm sure many of you must be knowing. It is extensively Research Rabbit is used for meta-analysis, for SRL. I mean, it gives a really very good data on these areas, the Research Rabbit. And then is your Dimension.ai, which is I use it for a different purpose. I basically, when on a particular area, I want to find out what is the research has taken place, what are the grants are there, what are the patents are there, and what are the different policy documents have come up. So when I have to find out the quadruple helix of any particular area, I generally use the dimensions.ai and all platforms. But so many, in today's sessions, we have discussed about so many tools and all, but choosing the right tool for the right research is the most important thing. That is the end of the day, I can say that. So see the science, understand the story, and shape the future for this. Thank you very much, and stay connected for our own sessions. Thank you very much. Over to you,
Thank you,
Uday.
sir. Very wonderful session and very informative. So as we come to the end of the today's enriching session, I would like to express our sincere gratitude to everyone who joined us and made the webinar meaningful, and your presence of participation is very. So now I heartfelt thanks to Dr. Juan Pablo Vascuer for sharing such a valuable insight on science mapping, visualization techniques, and research intelligence. Your presentation has truly uh, our understanding of emerging research trend and data-driven knowledge discovery. I would also like to extend my sincere thanks to Dr. Santanu Ganguly for his constant encouragement and guidance and support in making this webinar series a success. Now I kindly request all the participants to fill out the feedback form, which will be shared shortly in the chat box. Your valuable feedback help us to improve the future sessions and continue offering the meaningful professional learning opportunities. Please note that the e-certificate will issued only the participant who complete feedback form and meet the attendance requirement as per our guideline. Kindly submit your form before the leaving the session. And if
Uday,
you
would
have
you like
any,
to tell them about the rest of the whole week sessions which we are going to
yes,
have?
yes, definitely. So from tomorrow we have another interesting session. It's like we can say the from discovery to dissemination, AI across in research life cycle by Dr. Ujjwal Marjit from University of Kolani. Next session we have some research matrix, as well as we have counter usage matrix next session in Friday. And as well as it's a very innovative and you can say the useful for our library fraternity, that is our Dr. Sukhdev Singh, former Deputy Director General for NIC. He's have own presentation and AI in library operation. That will be very useful for next week in Monday. So now I request all the participants fill out that feedback form at your earliest.
Thank you,
And
Juan. Thank you, Pablo. That was fantastic, phenomenal. Your sessions was. Please share your PPT with all of us so that we can share it with the participants also. Thank you, Pablo, once again, and stay connected.
Thank
on
you.
behalf of
It was
HDFC
very
Library,
nice.
thank you once again for joining us today's webinar. And I thank to Dr. Juan Pablo Vascuer and Dr. Santanu Ganguly. It's a very informative and interesting topic on that today's era. And we look forward welcoming you in the next session of all the participants. Stay connected with us as HDFC webinar series. Thank you, all of you. Thank you. Please
Thank you,
fill
sir.
up all. Yes.
We will be sharing the PPT with everyone. As Yuan has said that he will send us the PPT, so we will send you the PPT also. And my PPT will also be available to each one of you.
I also already share it in the chat.
Yep. Oh, Acha, you already did it.
Yeah.
So Udan, please get it
Yeah,
downloaded so that we can search, send it to everybody.
we already
Yeah,
shared
I will
some.
send it.
Yeah.
Yeah. Thank you.
Okay. Thank you for
Okay,
everything.
thank you everyone. Thank you, wonderful session. Thank you to everyone.
Thank you. Thank you. Thank you. Thank you very much. Thank you, Pablo.
Thank you. Goodbye.
Bye. 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 Bye.
Bye.
Bye.